Here I'm going to go through the problem of finding the normal modes for a tetrahedron. And I'm not going to do this symbolically, which is a lot of work. I'm going to do this with a different approach, which is a brute force solution. So what I will do is I'll write the dynamical equations for a tetrahedron with 4 points. The 4 points will be at some positions, which I don't want to work out right now, but they will satisfy the equation that the force on each one will be given by the Hooke's spring law. So negative k times the equilibrium distance minus the length of the actual displacement between points I and j, pointing in the negative direction of the unit vector between I and j. So if our points live at vectors xi and xj, then here's the formula. The norm is the difference between the two, and this last component here is the unit vector for all of them. That's how we'll compute it in the code. All right, now to actually get the ground state, to find out what the equilibrium solution looks like and where the location of the points of the tetrahedron are, what we're going to do is we're going to just evolve the system using the dynamical equations, but we'll add some damping. So we'll add a term minus gamma times the velocity of the ith component that will reduce the energy of the system, and hopefully we'll find that it ends up in the ground state, which is the tetrahedron with the points and the positions that they should be in. All right, that's the strategy. Let's go ahead and implement this. So first of all, I'm going to import the plotting library, matplotlib, and then I'd like to animate this. So the second command here is for animation. I'm going to clear the output so that we can see what's going on. And I need to do a 3D plot, and so this is the 3D plot. I'll post a tutorial on doing plotting a little bit later, so you'll learn a little bit more about these commands, but that's it. Then we need the integration solver, the ODE solver, for solving the ordinary differential equation. That comes from SciPy. And so we've imported that. Now set up a few parameters. We'll use units for everything here. So the mass is 1, the spring constant is 1, the equilibrium length is 1, but you could change them here. All right, the first thing we need to do is we need to compute a function of the positions. And so we have to decide how we're going to organize our positions. And what I'm going to do is I'm going to store them in a single long array. So my positions will be stored like this: x0, y0, z0. That's for the first coordinate of the tetrahedron. And then we'll have x1, y1, z1, etc. for all 4 vertices of the tetrahedron. Continued. Okay, so that's what this x will be, and then from that we need to compute everything. So just so that we're clear, let me put this in. If we have, so we have 4 points in our tetrahedron, all right, and there are three dimensions, x, y, and z, and so the x dot shape will be 4 down and 3 across. Okay, so that's how big it's going to be. Now, when we compute the forces, we're going to accumulate them in a list for each of the particles. And so I will be the particle that we're going to accumulate the force for. And so I has to go from 0 till 3, so run over the 4 edges of the vertices of the tetrahedron. The initial force is 0, so we're just going to append 0 there, and then we'll update it in a little bit. Now for each of the other particles, we have to compute the force and then sum them all up. If I is equal to j, there's no force. The vertices of the tetrahedron do not exert a force on themselves, so we just continue, which means we skip out of the loop at this point and continue on to the next j value. Otherwise, we compute the displacement vector, xi minus xj. So notice what we're doing here in terms of the indexing. The first index corresponds to the particle. The second index corresponds to xyz. So we're taking the index of the particle, but all of the components, xyz. So this guy here is the position of particle I. And this is the position vector of particle j. And we're subtracting them to get xij, the difference between the two. I've put an underscore here to denote this as a vector, and then I will use the linear algebra function, the norm, which computes the length, and store that in xij. So now we simply go back up and we apply the formula that we have here for the equation for the force, which is negative k times the length minus L times the unit vector. And so here we have negative k times the length minus L times the unit vector, which is the vector divided by its length. So that's the force. we're updating the last force that we put into the list. Okay, that was what we did up here. Actually, let's make this a little bit clearer. So Fi equals 0, Fi plus equals this, so we add the new force to that, and then when we're done, we can go F dot append force I. So once we've accumulated it, we can append it to the list. And then we're going to return the list of forces and convert it back into an array so we can do some arithmetic on it. Okay? That's how the force function works. And this is the input argument. X looks something like that. All right, so now we have our force function. We should test it a little bit. I'll do that in a minute. We also want to see what's happening to the energy of the system, because as we run the simulation, the energy should decrease. And so we compute the kinetic energy, which is 1/2 v squared. So the dq will be the velocities here. The potential energy starts at 0, but we have to go through all the springs. So again, similar construct. For all the i's, for all the j's that aren't equal to I, we compute the displacement between the two. We take the norm of that, and the energy for each spring is k plus the distance between the 2 points minus L squared over 2. So k x squared over 2. That's our potential energy. Add them all up and return the sum of the kinetic energies and the potential energies. Now we need the right-hand side for the set of differential equations. That's fairly easy. We take our input. Now the ODE solver needs to have a simple flat array. So this will be a single long array with all the positions and all the velocities. So we reshape that into a three-dimensional array of 2 by 4 by 3. So remember, 2 here is the fact that we have q and dq. The 4 here is that we have 4 particles, the 4 edges of the vertices of the tetrahedron, and the 3 is the x, y, z. So we reshape this into the proper shape of 2, 4, 3, and then by default when we unpack, that'll act on the first index, so this 2 index, and the q's will be first and the dq's will be second. We have to mirror that structure when we return the results, that the dq's come first and the ddq's come second. All right, then we can go and calculate the force divided by m, add the drag term, or subtract the drag term rather. That gives us our ddq, that's the change in the velocity, and then put those together as usual for the differential equations. And now the ODE solver requires this all in a single flat array, and so we ravel the results. All right, so that's all we need to solve the problem, but we'd like to visualize this, so finally we create a plotting function. Again, we reshape the input into the 2, 4, 3 array, unpack that into the positions and the velocities. Further, we unpack the positions themselves into x, y's, and z's, so we can plot these. Now remember that once we do this unpacking, q and dq will have shape 4, 3, and the 3 refers to the x, y, z. That's why we have to take the transpose here, so the 3 index becomes the first index, and then we can unpack the x, y, and z. And then this is just checking to see if we're plotting in a known axis or we're creating a new axis. Again, same with the figure. If we don't have a figure, we get a figure. If we don't have an axis, then we create a subplot, and this is important in this case because we have to do a 3D projection. This is just a little bit of plotting detail that you can worry about later on. All right, once we have an axis, we call scatter 3D, which will plot the 3 points. The 4 points, the 4 edges of the tetrahedrons, and their x, y, and z coordinates. And then this is an ordering, because I want to draw lines between them that represent the springs. And so I'm going to plot a line from all the points, and I'm going to go from vertex 0 to 1 to 2 to back to 0, then to 3 to 1 to 2 and back. And this makes sure I traverse each edge at least once. Okay, that's how I draw the picture. Now we'll create a random seed, an initial condition. We need to create an initial state that's 4 times 3 times 2. It's probably better if I write this in the order of 2 times 4 times 3. It doesn't really matter though because it's flat at this point. So random positions, random velocities, create a figure and axis object, and we start our simulation with a time step of 1 in our units. So 1 natural time unit, which will be determined in terms of k and m. And then we just create a copy of our initial position. This is our energy. And the function, if you remember, the right-hand side required an argument gamma, which was the damping factor. And so we're specifying that here. We're going to give it a damping factor of 1. Now, we start at time equals 0, and we run a loop until the energy is less than 10 to the minus 8. Okay, so while the absolute value of the energy is greater than 10 to the minus 8, what do? We increase the time. We then call the ODE int solver from the previous time to the current time using the previous x, and that gives us the new x. The right-hand side is the function, and we pass the arguments, which has the damping factor in it. We extract the -1 here because the ODE int function will return the solution at t0 and t1, and we only want it at t1, so we just want the last one. We set the old time to be t1, and now we just go and plot. If we have an axis, we clear it, we plot the figure, and then we compute the energy for the state, and we add that to the title of the plot, and then we display the plot. This is important if you're using it in a notebook, because this will force the figure to be drawn, and then clear output will clear the output so that you don't get 5,000 copies of the figure. And it's one figure copy. So just take this right now as what you need to do if you want to animate output in a notebook. I'll talk about that in another tutorial at some other point. The wait equals true is important because it will wait to clear the output until we draw something again. All right, let's run this and see what happens. Okay, so we see as it's evolving, we're getting close to the shape of a tetrahedron, and the energy goes down to something very small. Let's try again. So we're starting with a fairly large energy. As it's evolving, it's oscillating a little bit. The oscillations are being damped, and now we've ended up at a tetrahedron. If we change the seed that we use to generate the random initial condition, we should end up with a slightly different shape, and it ends up in a different configuration. Okay, so the configuration is random, but we end up with a zero energy state. We expect this to be zero energy because the springs are at equilibrium length, and there's no potential energy, and the kinetic energy goes to zero as well. All right, now let's find out what the normal modes are. So to this solution, we're going to add a random perturbation. Let me create a seed once more so that we have reproducible results. All right, so we create a random perturbation, and then what I'm doing here is I'm setting all the velocities to zero. So this is simply setting the positions to some random displacement. I take my solution that I computed above, and I'm adding a small displacement to that. I'm going to evolve this to t equals 500 at 2 to the 9 points, linearly spaced, and I can just call ODE int once, start with my starting solution, which was the perturb solution, evolve it, and that will give me the solution. It'll take a little while to run. There we go. Now, I don't really want to plot everything here, but let's briefly show this. So I'm plotting all the x's, and you can see they basically move in a straight line here. They don't move much, and the reason is I give a very, very small displacement. Now we need a small displacement because we want to talk about normal modes, not nonlinear excitations, but let's just see what happens if I give it a really big kick. So if I give it a really big kick, you can see there's lots of fluctuations there. That's a little bit too big. Let's make the kick a little smaller. And what we're going to do now is we're going to take these signals. You see how they have oscillatory components, but there's obviously some interference. And we're going to Fourier transform these and try and figure out what frequencies are present in all of these components. All right, so that's what our next step is. Let's go back to the very small kick. All right, so for each x, we're going to plot what's called the power spectral density. And so take the P, if you want to see what this does, you can take the PLT PSD function, put a question mark after it, Shift Enter, and the signature and all the details will be shown down here. This computes the Fourier transform. It does it at a certain sampling frequency, shows you the frequencies, and then plots it very nicely. It also does some windowing to deal with the fact that our signal is not actually periodic. So I'll let you look at that. The important thing here is to give the correct sampling rate, the number of times divided by the total times we have. We need to remove a trend. If we did not detrend the data, then there would be a large zero component frequency. So you can see it over here. That's because with the system, the center of mass probably is now been displaced, or we might have some rotation. So detrend removes all the linear trends, which gets rid of that zero mode. And we're left with 3 sharp peaks. So there's definitely 3 normal modes in the system, and if you work this problem out, you can find that the normal frequencies are k over m, 2k over m, and 4k over m. That's omega squared, so take the square root of those. Now, those are the angular frequencies. We need the linear frequencies, so we divide by 2 pi, and then we're just going to draw a vertical line at each of those points, and indeed we see that those vertical lines line up exactly with the points here. Now there's a whole bunch of curves here because we've done this for every single point. We've looked at the x, y, and z position of each of the points. The signal is the same for all of them. These normal modes, we've randomly excited the system, so they all couple, they're all excited. It would be very hard not to excite them if you use a random perturbation, and so we indeed see that there's power at each of these three frequencies, and they match the analytic formula. So this is a brute force way of trying to find the normal modes of a tetrahedron, and a good way of checking your work without too much. You don't actually have to work out the geometry of this problem, which is a little bit tedious. Okay, hope you enjoyed that.